In this problem, we are looking at something a little different. We are given the first derivative of a function, and we don't actually know the original function itself, and just its derivative. And we are asked to find the second derivative and then sketch what the original function f roughly looks like. Let's start by finding the second derivative. I've done the calculations beforehand, and the second derivative looks like this, actually. From here, we need to look at where these derivatives change signs. The places where the first derivative change sign gives us our local maximum minimums, our critical points, and the places where the second derivative change sign gives us our inflection points. So from the first derivative given by the problem, it's easy to see our critical points are x equal to 0. We can do it like, just write it down like x minus 2 and x minus 5 squared. Then our critical points are x equal to 0, x equal to 2, and x equal to 5. And now for the second derivative, let's set it as equal to 0, and the roots will be x equal to 5. We have the obvious one, but we also need to find the roots of this quadratic part here. And let's find the roots of this quadratic term. And to make it easier, I'll divide the whole expression by 2. So this will be, and I want to solve this by completing the square. I know that x minus 2 square is x squared minus 4x plus 4. And to match my expression, I look at the constant here. I want 4, but I have 5 over 2. And 4 is just equal to 8 over 2. So I'm going to add and subtract 3 over 2 to both sides. Then this will become x squared minus 4x minus 3 over 2 is equal to 0. And I'm going to replace the 3 over 2. And this will become x minus 2 squared is equal to 3 over 2. So I'm going to take the square root of both sides. And please don't forget the plus minus. And we get x is equal to 2 plus minus root 3 over 2. So our imported points from the second derivative, the places where concavity might change are these 2 points where x is equal to 2 plus root 3 over 2 and the point x is equal to 2 minus root 3 over 2. And of course x is equal to 5. Now we have all our x values. So let's set up the sign table. What we have 0 to 5 and here 2 other points. First we need to put them in order. How? First I'm going to draw my table. And I'm going to write down all the points, 0 to 5. Okay. First 0, then 2 minus root 3 over 2, then 2, then 2 plus root 3 over 2, and finally we have 5. And let's mark where each derivative equals 0. First derivative is 0 at 0, 2, and 5. And second derivative is 0 at this point and 5. Okay. Let's check the signs for the first derivative. Okay, we can see our first derivative now. If we test a number to the left of 0, like a negative number, the first derivative is positive. You can see that the first term will be negative, second one will be also negative, and this term is always positive, so negative times a positive, this will be positive here. And at x equal to 0, it has a single root, so it flips to negative. It stays negative and then flips to positive at x is equal to 2. but pay attention to x is equal to 5. Because of the squared term, as you can see here, we have a double root in the first derivative, so it does not change sign here. It touches 0 and stays positive. We have a double root here. Okay, now for the second derivative, we can easily plug x equal to 0 into our second derivative to test that region. And it gives me a negative value. Since all the roots we found for the second derivative are single roots, and the sign will simply alternate at each of its zeros. So it starts with negative, then positive here, then negative, and positive. So with our table complete, we can see exactly how our original function f behaves by combining our increasing decreasing trends from our first derivative and with our concavity from second derivative. Let's draw. Okay, first increasing and concave down, just like that. Next, decreasing and concave down, just like that. Then decreasing and concave up. Okay, after x is equal to 2, it's increasing and concave up. Okay, then increasing and concave down. And after that, finally, it's increasing and concave up. We clearly have a local maximum at x equal to 0 here. And we have a local minimum at 2. The places where the concavity flips are inflection points. Like here in our points where 2 minus root 3 over 2 is an inflection point. And also 2 plus root 3 over 2 is an inflection point. And also the point where x is equal to 5, it's also an inflection point where the tangent line is perfectly horizontal. Now let's put it all together on a graph. Okay, but remember, since we only started with the derivative, we don't know the exact y values of the original function. So the actual graph could be shifted way up or down, but the shape, the locations of the maximum, the minimum, the inflection points, and the horizontal flat spot at x equal to 5 are all perfectly correct. And I'm going to draw how roughly our function looks like. First start with some random point here, and we're going to increase with concave down like this. Maybe use another color. Okay, just like that. Then we have a local max at x equal to 0. And we're going to decrease concave down. Okay. And after that, we have an inflection point. Great. Now we come to the point x equal to 2. We have a local minimum here. And after that, we are going to increase with concave up. Just like that. After that, we have another inflection point. Great. And we came to the x is equal to 5 part, the horizontal flat spot, with our inflection point like that. Okay, so let's move it like that. So this is where the 0 is. This is okay. This is 2. Sorry, I think I missed one. Oh, I just shifted, I think. Okay. So I started with random point, so this will be 0. This will be 2, our local min, and these are my inflection points. This is 5, and these are the other 2 inflection points. Okay, so this is roughly how our function f looks like. And we are done.